Welcome, human. We have brought you here in hopes to share our knowledge on behalf of our dear sick friend Earth, who I'm sure you can tell is not in her best condition.
What? Who? You?
Oh yes, dear, over here. I'm talking to the moon. Our dear friend Earth needs your help spreading the truth to mankind. We're counting on you, Dr. Seisman.
Sorry, who?
You're not Dr. Seisman? No? I'm sure you'll do. Let's begin. Waves are disturbances or vibrations that transfer energy from one place to another. In physics, there are many types of waves, such as sound waves, light waves, and water waves. But when it comes to Earth, the most important are seismic waves. Seismic waves are vibrations that travel through Earth, usually triggered by earthquakes. The science behind earthquakes. Most earthquakes are caused by sudden movements of tectonic plates, which are massive sections of Earth's crust that float on the semi-liquid mantle. These plates are constantly moving, and when they grind against each other or get stuck due to friction, stress builds up. Eventually, this stress is released in a burst of energy. This is the earthquake. Let's take a look at the interior of the Earth. First, we have the crust, the thin outermost layer where you live. It's made of solid rock and is broken into tectonic plates. Next, we have the mantle, which is a thick semi-solid layer beneath the crust. The upper mantle is partly molten, allowing plates to move. We have the outer core, which is made of liquid iron and nickel. It affects how certain seismic waves travel. Last but not least, we have the inner core, which is a dense, solid ball of iron and nickel at the center of the Earth. Seismic waves behave differently as they pass through each layer. This leads us to our main question. What can seismic waves tell us about the interior features of the Earth? And how do they explain why the Earth shakes? When an earthquake occurs, it sends out seismic waves, vibrations that travel through the Earth carrying energy from the source of the quake. These waves are like messengers. There are two main categories for seismic waves: body waves and surface waves. Body waves that travel through the Earth's interior. These waves move through the inside of the Earth and arrive first at seismic stations. We have the P waves, known as the primary waves, which are the fastest seismic waves and the first to be detected. They travel through solids, liquids, and gases. We then have the S waves, which are the secondary waves, slower than P waves and second to arrive. They only travel through solids, not liquids, and move in a side-to-side motion. Next are surface waves, which travel along the Earth's crust. These waves move along the surface of the Earth and usually cause the most damage during an earthquake. We have the love waves. They move the ground in a horizontal side-to-side motion and travel faster than Rayleigh waves, but only through the crust. Next, we have the Rayleigh waves, which cause both vertical and horizontal ground motion in a rolling elliptical pattern. They move like ocean waves, causing the Earth to ripple. Here are the key properties of seismic waves: their speed, their amplitude, the path, and the region of sensitivity. Now let's learn how scientists use seismographs in seismology. Seismologists are scientists who study earthquakes and the seismic waves that cause them. To detect and record these waves, they use an instrument called a seismograph or seismometer. A seismograph works by having a suspended mass with a pen attached, which records vibrations on a rotating drum or digital sensor. When the earth shakes, the frame of the seismograph moves with the ground, but the mass remains still. By analyzing seismographs from different locations, scientists can determine the origin of the earthquake, the magnitude or strength, the depth of the earthquake, and the internal structure of the earth, since seismic waves travel differently through different layers. Seismology also plays a critical role in early warning systems, where quick detection can give people precious seconds to take cover before stronger shaking arrives. Now, let's take a look at real-life application of seismic wave study, shall we? You see, seismic waves aren't just useful for studying earthquakes. Here are a few important real-life applications: earthquake engineering, tsunami warning systems, resource exploration, and nuclear test monitoring. These applications show how the study of seismic waves goes beyond understanding. It helps save lives, protect structures, and even ensure global security. But of course, there's always a good and bad side to everything. Let's go over the negative and positive effects of seismic waves. Negative effects. Ground shaking can collapse buildings, damage infrastructure, and cause injuries or loss of life. Dear. Earthquakes can trigger landslides, avalanches, and tsunamis. Strong seismic waves can break power lines, water pipes, and communication systems, disrupting communities. Positive effects, on the other hand, include seismic wave data gives a scientist critical insight into the Earth's internal layers. It also helps in planning safer cities and enforcing better construction codes, and allows countries to prepare and build early warning systems to reduce future risk. Now here are some safety tips during earthquake. Take note. Number 1. Drop, cover, and hold on. Get under a sturdy desk or table. Number 2. Stay away from windows and objects that could fall. Ooh. Number 3. If outdoors, move away from buildings and power lines. Number 4. If driving, pull over safely and stay in the vehicle until the shaking stops. Well, that concludes it. Tell your Earth friends we said hi. And don't you wait around for another natural disaster just to learn something new. And don't forget to visit. I'll try.